Alright, welcome to another AQA A-Level Chemistry video. This is going to be the part 3 of the series where I'm talking about exam questions on acids and bases and buffers. And this video I'm going to be talking about one slightly longer question. It's a 7 marker. This particular one's an 8 marker, but usually in your exams you see it as a 7 marker. But it's to do with calculating with buffers. So this video I'm going to first go through a little overview of what a buffer is and how the understanding it is very important to understanding making assumptions for calculations. And then I'll actually go through one of the questions, and I'm not going to go through, as I said, in this series I'm not going through them in exam conditions. I'm just going to go through them and explain them to you, and then maybe in another video or in the future I'll do it in exam conditions. But this video in particular is just me talking to you about how to answer that question. So without further ado, I'm just going to go straight into the video. So I think we all know, right? There's all the we're very aware of what a buffer is, but by this point, if you haven't, I'm probably not going to leave a link in the description to the videos. But if you look at my previous videos on this topic, I've done videos on what a buffer is. So if you don't know what a buffer is, check that out. But assuming that you understand what a buffer is, you know that a buffer requires a if you're doing an acidic buffer, you need a weak acid and the salt of the weak acid, right? But there's ways that we can form that without we can form buffers by not just doing weak acids and weak base. We can actually form a weak acid and a weak base, because not much just goes into actually explaining how we actually form the buffer, right? We can actually form buffer. If you want to talk about an acidic buffer, right, we can form an acidic buffer with a weak acid and a strong base. Now remember, an acid base reaction, right, is also known as a neutralization, is when you have acid plus base, and you would know that forms a salt and water, right? That is the understanding of what a buffer is, where you have an acid plus a base goes to form salt and water. Now I want you to think of this acid now as being a weak acid and a strong base. Now you still get a salt and water, but what you don't, if you change the concentrations and the volumes of the amount of acid and base we can use, we would still have some excess acid left over, and we'll still have the salt left over. Now this is an example of what I mean now, and this would actually allow us to form a buffer, because we wouldn't have just the salt in here anymore. We'd have a salt and we'd have a bit of weak acid left over. So therefore, and it would be that salt will be the salt of that weak acid. Now what do I mean by this, right? So say we had, and that is the buffer, right? That's what we'd have. We'd have the salt and the weak acid still left over. So say we had an excess of a weak acid. In this case, I'm using butanoic acid and a strong, and then I'm having a small volume of strong base, considerably low. You can see the difference between the two here, right? The strong base is significantly lower in concentration, but we know that strong bases is still pretty capable of neutralizing a strong acid, even though it's in a lower volume and it's not in excess. It's very, very strong in to neutralize with acid, right? Especially a weak acid. So if I reacted an excess of weak acid, or this butanoic acid, with this strong base of potassium hydroxide, right, what would happen is that we know that potassium hydroxide, because it's not in excess, we have a measured volume of potassium hydroxide, right? We probably know the concentration as well. All of this is going to be reacting with an excess of the butanoic acid. Now, why is this important that we know that this is the limiting, that this is the going to fully react? Now, we know that this is in excess, and now I've mentioned several times, but I'm just making sure that you guys understand what I mean here. Because this is in excess, and this is not in excess, we know this is going to fully react. We can therefore, we say in science that this is called the limiting factor, because all of the potassium hydroxide will fully react in solution when it's reacted with the butanoic acid, but not all the butanoic acid will react with the potassium. So yeah, not all of the butanoic acid will react in this case, because any of it that's reacted, right, we'll only know that only some of the butanoic acid will react with the potassium hydroxide, and the rest hasn't got anything to react with, because all of the butanoic acid, all of the potassium hydroxide has been reacted with if we mix them two together, right? So if we mix these two together, all of the potassium hydroxide will be used up, right? And this is good for calculating. It's important that we know that the potassium hydroxide is the limiting factor, because it's good for calculating, as we'll see moving forward. I'll show you why it's important when I go through a question. But now what happens is that when all of the potassium hydroxide has reacted, you then get to this point here. I'm sorry if I'm moving a bit too slow. I'm just making sure that you guys can understand what I'm saying. If I'm going too slowly, leave a comment in the video so I can just go through a bit more quicker, but in case some people don't get what I'm trying to say here. So we then form this here. We'd form this, right? Where we have the salt, in this case would be potassium butanoate and water. But realistically, we only have a certain content, a certain volume of this is going to be our potassium butanoate. Really, what we have in this solution here is potassium butanoate plus some water plus, really it's not really water. What we actually really have here that's left over is our butanoic acid, right? Hopefully you understood why I'm saying there's still some butanoic acid left over, because this salt here is formed from the potassium hydroxide reacting with the butanoic acid. So therefore we can assume, right, that this, therefore the concentration of potassium, all of the potassium hydroxide is reacted, and any potassium hydroxide that's reacted with our I actually write the equation here, right? Oh. All right, here. So our butanoic acid plus our potassium hydroxide goes and forms our salt, which is the potassium butanoate. The reason I write this out is to help us, because we can actually make an assumption for this, which actually can be useful for calculations, and then plus some H2O left over. We always have water left over, right? But we know that potassium hydroxide is a strong acid, is going to fully react because it's the limiting factor here, right? So therefore, we can assume that this concentration here is the same as this concentration here, because all of this that's reacted will form the salt. And because this is in excess, technically we still have some, because remember, only this amount of butanoic acid is going to react to form the salt. The rest is just left over, really, right? So we still have some butanoic acid left over, technically, in our solution here. So if that's the case, right, if we have the salt of the weak acid and a weak acid, that is what an acidic buffer is. And that's what we have here. We've now formed a buffer. We've formed a buffer here. I probably should have colored this a bit differently. Sorry if it's a bit much here, right? But we have now a buffer, right? And that's what's happening. And hopefully this made sense what I was saying, because this is what's actually happening when we actually do some of these reactions. Because this, when we remember, you can react you can actually titrate a weak base, a weak acid with a strong base, and it looks like looks like this here, right? if we were to titrate, this is what we'd see. We'd see something like this, right? So if this is the apparatus that we'd use, go right. But on a graph, you'd see it more like this, right? Where you have this little period here, and this period. That's our. It's acting, because we have this is such a strong base. It's only until up until this point, up until you get to here, right? The pH is still gonna be, the pH is still gonna be and what I mean by this is that if we're adding it, right, if you're adding this together, it's roughly here, right? But until you get to roughly that point there, I mean, what I mean by this is that you've added this amount to here, right? So that's going to be up to here. But until that point, it's the base is actually acting as a buffer, because you're adding acid, but we've already formed, we're forming our potassium butanoate, and we still have a weak acid there, or we still have more hydroxide ions than acid, so it's acting as a buffer up until that point. Once you've added more, we've gone above this value here, right? Once we've gone above this value here, and we have more, it reaches a point where there's so much more acid than base, we go over this equivalence point here, and now we're here. And now we formed this in our solution, potassium butanoate and our butanoic acid. We've now had an acidic buffer, and we can maintain this pH here. This actually we can maintain. If we want to reverse this reaction, go back up again, fine. But we actually now formed a buffer, and that's why we keep this pH here. So this is what. So if you're ever wondering why there's such drastic changes in pH, right? Why it's not a gradual curve like that, it's because we're actually forming, technically, our acids or our bases are acting as buffers in that scenario. Yeah. So this is the two, and that when you form this, right, I want to bring this point back here, right, where I know I've put a lot of writing here, and I should probably, yeah, I'll probably take this part out here. I'll bring this down because this is the most important thing for me here, right? Or I'll bring it here. So once we formed the buffer, we have our salt and we have our weak acid, right? Remember, we have, bringing it back to this, right? We've formed our potassium butanoate with our weak acid, which is our buffer. So in our solution, we have our our weak acid and the salt of our weak acid. So remember, we know that weak acid weakly dissociates H plus ions in solution, or they weakly dissociate in solution. So therefore, we can make the assumption in saying that, well, we know, it's not an assumption, we know equilibrium is not far to the right, it's more closer to the middle. And therefore, because it's not, there's a lack of dissociation, which explains the lack of dissociation. So there's a high concentration in solution. We'd expect to have a high concentration of our undissociated weak acid in solution, and a low concentration in this case from this dissociation alone, from the top equation alone. We expect a low concentration of butanoate ions from that dissociation, and a low H plus concentration. Whereas we know salts fully dissociate in solution, and I write salts like this, right? I write salts I write salts like this. Sorry about that. Like this, because it's not a full. It's more like an ionic interaction. It's not a full-on ionic bond, because this wants to dissociate anyway. You'll rarely find salts like this above here, because that's gonna instantly fully dissociate in solution, right? So that's why I write the COO minus and then a K plus, because really, because it dissociates so readily in solution and so easy in solution, equilibrium is far to the right. So therefore, we'd expect to see a high concentration of our butanoate ions, and a high concentration of, sorry, that should be K plus. I'm really sorry about that. That should be K plus. and a high, so you expect to say a high concentration of butanoate ions from this dissociation, and a high concentration of potassium ions, and we therefore would expect, because this fully dissociates, because the salt fully dissociates, a low concentration of our salt. So remember, we said that because we know, if to bring this back, right, we said that from this reaction, the potassium hydroxide is acting as a limiting factor because it completely gets used up in the reaction. It completely reacts with all of the acid, right, in the neutralization to form the acid. So therefore, because of that, we said it's a limiting factor, and it's actually good for calculations. And I said the cell's going to explain the reason why. This is good for calculation because we know potassium hydroxide fully gets used up. We can assume and it gets used up to form the salt. Therefore, we can assume that the concentration of potassium hydroxide is the same as the concentration of our salt. But so we know this is to be true, right? But we also know that salts fully dissociate in solution. Therefore, we can make the assumption in saying that the concentration of our salt is the same as the concentration of our A minus. In this case, our A minus is CH3 CH2, our butanoate ion, right? Our butanoate ion. CH3 CH2 CH2 COO minus. Therefore, the concentration of our base is equal to the concentration of our salt, which is also the same as saying it's the concentration of our A minus. In this case, A minus represents our salt. And this is very, very good for calculations because it allows us to make a load of assumptions and that we can use to help out for our calculations, whether for pH, working out Ka. And I'm going to go through an example here. So I've already technically answered this question, so I've got an already prepared answer at the end, but I'm going to go and explain to you how I went through it, but I'll leave a little, I've left a little slide at the end to show you how I went about it. So, right, so this question here, right? I'm going to go through this question. It's 8 marks, but I'll go through each and every stage. I'm not doing this in exam style conditions. I know I'm probably speaking way too much. I'm sorry if I am, but I'm just trying to make sure that I don't confuse people because I think sometimes I confuse people. So anyway, so we have 550 centimeters cubed of a buffer solution of pH 3.8, and it contains 0.940 moles of propanoic acid, where the Ka is 1.11 times 10 to the power of minus 4, and 0.68 moles of sodium propanoate. Now calculate the change in pH when 20 centimeters cubed of 1 mole per dm cubed HCl is added. Okay, 8 marks. Okay, so there's a lot of information here. A lot of information. But when you, I've already said this multiple times, if you want to understand any topic, you need to do a lot of exam style questions because that's the best way to understand a topic. Knowing the content doesn't mean shit. Sorry, but it's true. You can know the content very well, but if you don't know how to answer questions, it's pointless. And the more times you answer these types of questions, the more easier it is. And that's why the pH is one of my favorite subjects, because it's a lot of marks. There's a lot of long-winded questions, but they're very easy. They're all pretty much the same kind of thing, right? And I'll go through it here. So a lot of information here. I'm going to break it down. So the first thing I'd actually do is we need to actually understand what's going on, right? So we have a buffer solution. We have a buffer solution here of propanoic acid and the salt of our weak acid, which is propanoic acid, and the salt of the weak acid, which is sodium propanoate. Right, so that's our buffer. They already told us the pH. This is the pH of this buffer that's maintained. So what's happened is that we already have a buffer here, but we've added 20 centimeters cubed of 1 mole per dm cubed HCl to this solution, right? And now the pH has changed. Now we want to work out what the new pH is so that we can work out the change in pH. That's actually what the question is, right? Actually, I'll use different highlighting color so you can see what I mean here. We're trying to work out what the change in pH is. That's the actual question. So how are we going to go about that? So we need to actually understand what's going on here. So what I always do, you don't have to do this, but what I always do is to write out the equations. Now, you don't get any marks for writing out the equation, but it's pretty useful when answering questions when you write out the equation, because it just gives you an idea of, you can annotate your equation to add anything that you want to add that maybe help you in your calculation. Say, okay, I'm talking about this here, this many moles, is this decreasing, so and so. I always write it down. It doesn't take you many minutes. It takes you a couple of seconds to write it down. You already know what it is, right? So our two equilibrium equations, right, are going to be the dissociation of propanoic acid into propanoate ions and plus H plus, and then you have our salt, which is sodium propanoate. Oops, sorry. Right, so this is what's in our buffer solution in itself, right? That's what's happened. This is inside the beaker, the buffer. Before we add any acid, this is what's in our bus. This is the two equations that's happening, similar to the one I just said above here, right? Okay, so the first thing I'm actually going to do here is I'm going to work out the moles of the acid that we're adding, and there's a reason why, because we need to work out. There's clearly a change to the concentration of H plus in our solution, and that's what causes a change in pH, right? Okay, so let's work out what we actually have. So I'm going to focus on this part first. So work out the moles of acid. So concentration is equal to moles over volume. Therefore, moles is equal to concentration times by the volume, right? So then the moles of HCl is equal to what's the concentration again? So yeah, so 1 times by zero. I can see from here it's just 0.02. But remember we have to convert our volume from centimeters cubed to decimeters cubed, and that's just going to be volume of acid. Let me just scoot this down. Sorry, scoot that down. Oh, have I done something wrong there? Oh, I know what I've done here. Right. So volume of acid, I can just see from here is just 20 times 10 to the power of minus 3, or dividing it by 1,000 to get from centimeters cubed to decimeters is just timesing it by 1,000, or 10 to the power, or timesing it by 10 to the power of minus 3, same thing. Decimeters cubed, right? So 1 times by 0.02 is obviously just equal to 0.02 moles. So we're adding 0.02 moles. Okay, so we have that information now. Again, I know I'm going slowly through this, but I'm just trying to explain for you every single point. If you just want to skip to going to every point and don't want to hear me talk so much, you can just skip ahead. Don't feel like you need to pause and watch me, but I'm just trying to go and help you guys. So there's one thing I actually forgot to mention, which is actually probably before this step, right? I forgot to write out this equation. This is the second biggest equation, really. You really should know this. So we should write out what the Ka is, because we know they've given us Ka here, so I'm assuming I'm going to use Ka at some point. So we know that Ka, for this occasion here, it will be H plus. K is related to this equation. The Ka is talking about the acid dissociation constant, which is what the K is. So it's going to be talking about that equilibrium constant there, right? So it's going to be, obviously, any equilibrium constant is obviously your products over your products over your reactants. So K is equal to H plus multiplied by CH, or your propanoate ions, right? CH2 COO minus over propanoic acid. The reason why I've done this is not just for the sake of just saying, just writing out for the sake of doing it. There's a reason for this, because we want to work out the pH, right? In order to work out the pH, we need the H plus. Remember, we're trying to work out the change in pH. In order to work out the change in pH, we need to know what the new pH is. And in order to work out the new pH, we need to work out the H plus concentration. They've given us the Ka. We need to work out the H plus concentration. So we need to work out what the A minus is in this case, and our HA. We need to find out what that is. So once we work out this and this, we can rearrange our equation to work out what H plus is. So that's why that's useful there. So equilibrium moles. We've added 0.02 moles to our solution, right? What does this mean? We've added 0.02 moles of acid to our solution. So what does that mean? So there's a new in equilibrium, there's new equilibrium moles. We need to work out how much moles we have in equilibrium. So what's actually happening in here is that, think about it, right? So if we're adding acid, in this case, we're adding a strong acid, which is HCl, with increasing our H plus concentration. That's what's happening, right? HCl is a strong acid. One has to just consider it as being an increase in H plus, right? So therefore, we're increasing 0.02 moles of H plus, right? So the H, let me actually highlight it here in red, right? H plus concentration is increased by 0.02 moles. What does that mean? Well, how does that affect our reaction? Well, if we're increasing, remember, we have to think about it as an equilibrium. Think back to Le Chatelier. If you increase the concentration of your products, how does that affect your equilibrium, right? It causes equilibrium to shift to the left to reduce the concentration of products. So that's what's happening here, right? So we're increasing our moles of H plus by 0.02 moles, which causes equilibrium to shift to the left, right? Equilibrium to shift to the left to reduce the mole. So by doing so, we're going to decrease our concentration of propanoate ions by 0.02 to increase our moles of propanoic acid, right? So if we're increasing our H plus concentration by 0.02, equilibrium shifts to the left to increase the concentration of propanoic acid. So propanoic acid increases by 0.02 because equilibrium is shifted to the left. And if that's the case, that means that, but these are both the same thing, right? These are both propanoate ions. Therefore, if that's the case, if equilibrium shifts to the left to increase the moles of HA, or the propanoic acid, by 0.02 moles, therefore the concentration, we're decreasing the moles of propanoate ions by 0.02 moles. And if this is a bit too difficult for you to understand, I'll represent this like an ice table. Because I can. You don't have to write it like an ice table, but I will do it, right? And it's an ice table that's going in the reverse direction. So I'll write it in the reverse direction. So we have, I'll write out here, propanoate ion CH3, CH2, COO minus, plus our H plus, and with that goes to form, right, our propanoic acid. So let's treat this like an ice table, right? We don't have to. I can just do this without doing it as an ice table, but I will just do it as an ice table for the sake of people that may not see it like that, because maybe it's a bit easier for you to understand ice tables. So we treat this as, we already know our initial moles of propanoate ions and propanoic acid, because it tells us in the equation, they told us in a question that we have 0.94 moles of propanoic acid. So that's our initial moles of propanoic acid, 0.94 moles of propanoic acid. And they tell us as well that we have 0.68 moles of sodium propanoate. But we know sodium propanoate fully dissociates in solution to give us our propanoate ions and our K plus. So we can assume that we have 0.68 moles of sodium propanoate. 0.68 moles of sodium propanoate. Now, realistically, we're trying to, because this is the increase in H plus concentration, equilibrium shifts to less, we're going to decrease it in our moles of H plus, right? So what's actually going to happen is we have X moles of H plus. We don't actually need to know the moles of H plus. We're not really looking at that. Remember, we're only trying to find out, we're only trying to find out what our HA and A minus is. We're trying to use that to help calculate for H plus. So we're not really interested in finding out the moles for H plus. We're just trying to find out the concentration of HA and A minus, so you can just work out the concentration of H plus directly, right? So in this equation above, right, though we've increased our moles of H plus by 0.02, equilibrium is shifted to the left to reduce that concentration. So the moles of H plus is actually going to decrease by 0.02. So our products is going to decrease by 0.02 moles, right? Hopefully you understand what that means. If you didn't understand what that means, leave a comment in the video. I'm decreasing the moles of all of our products by 0.02 moles in this top equation. So therefore we have our changes minus 0.02 moles, minus 0.02 moles, and we're going to increase our reactants by 0.02 moles. So it's plus 0.02 moles here, and therefore so we have 0.96 moles of propanoic acid and x minus 0.02. We're not really interested in that, but we have 0.66 moles of propanoate ions. So how I like to represent it like here, so moles of propanoate ions. Notice I put closed brackets or curved brackets for moles. I never represent moles if square brackets, because remember square brackets are only representing concentration. So moles of propanoate ions, COO minus, is actually equal to 0.66, or the equilibrium moles of propanoate ions is 0.66 moles. And the moles of our propanoic acid, again, if anyone has any comment, anything they want to say about my videos, about how I can improve them, or you don't like them, or maybe they're a bit long, just leave a comment in the video and I'll try to explain to you. So that's 0.96 moles. So yeah, so we have in equilibrium we have 0.66 moles of propanoate ions and 0.96 moles of propanoic acid. Right, so that's useful now. So we have the moles now, right? But we need the concentration. So what do we do now? We need to find the total volume of our solution. Now we know that we have 550 centimeters cubed of the buffer solution, and we're adding 20 centimeters cubed of H2O acid, right? So that means we just add them together. So it would be 550 plus 20 is just 570 centimeters cubed of our total solution. But remember, this is in decimeters cubed, so we'd have to do 570. Sometimes you can just see it directly, but if you can just write 0.57, but 570 times 10 to the power of minus 3 equals to 0.570 decimeters cubed. If you really want to go through a long method of doing, saying 550 times 10 to the power of minus 3 and 20 times 10 to the power of minus 3, 0.55. Again, you don't have to do this. 0.02, then in saying that the total volume of solution, again, I wouldn't do it. The more you do these questions, the more you can see it, is equal to 0.55 plus 0.02, and that'd be equaling 0.57 decimeters cubed. And that was the step for, actually, I forgot to mention I'm doing it in steps, right? I'm doing moles of acid in that step 1, step 2 was equilibrium moles, and step 3 was the total volume of a solution. 1 second. I'm just, sorry, I'm streaming at the same time, so just please bear with me. I'm actually streaming in these videos. Maybe I shouldn't be streaming when I'm doing these videos, but yeah. Anyway, so now we've now worked out the total. We have the total volume, we have the moles. Now we just need to work out the concentration. Remember, concentration is equal to the moles over the volume. So the concentration of let's just go for the propanoate ions because it's right there. Concentration of propanoate ions, CH3 CH2 COO minus, is equal to what was it? 0.66 over 0.57. So 0.66 over 0.57, whatever that equals. And then our concentration of propanoic acid, CH3 CH2 COOH, that's equal to 0.96 over 0.57. And then I'll just get my calculator here. Put that into calculator. I actually forgot to mention this is 0.660, three significant figures. The reason why the lowest number of significant figures in our question is actually three significant figures. As you can see in every example, it is all three significant figures. So we would use three significant figures there. So forgive me for that one. 0.66 over 0.57. That's 1.16. 1.16 moles. And then 0.96. That's 1.68. Rounded to 1.68. Sorry, did I say moles? I meant to moles per dm cubed. Moles per dm cubed. That's our concentration now. Now the next thing now is to actually calculate the H plus concentration. Now how we're going to do that? We just rearrange this equation here. We've now got everything we need. We just need to work out the H plus concentration. So H plus, in this case, to rearrange that equation, would be equal to Ka multiplied by our HA, which is a propanoic acid, CH3CH2COOH over our A minus, which is the propanoate ions, CH3CH2COO minus. And now that's it. We just substitute our values into our equation. So H plus is equal to, let me just double check that would be correct. It would be, yeah, it was that. That's correct. I'm just looking back if that was making any sense. And now we just substitute our values in. So our Ka, they told us our Ka is 1.11 times 10 to the power minus 4, as seen here. Put in the blue. Ka is 1.11 times 10 to the power minus 4. So 1.11 times 10 to the power of minus 4. And that, what's our H plus, our propanoic gas is 1.68, sorry, 1.68. And then I think you can already see what's going on here, sorry. I should have had a drink of water before doing this video, sorry. And then that's equal to whatever the hell that is, right? I think I've made that power a little bit too large. Obviously, in a real exam, do this much quicker than I'm doing it. I'm just doing it because, I don't know, man. I don't know why I help you guys. I don't know why on earth I do this. Life's tough, man. Right, so that's going to be 1.61 times 10 to the power minus 4. Moles per dm cubed. And that's our H plus concentration. Now we need to work out the pH. We now have the H plus concentration. We now need to work out the pH. So our H plus concentration, so our pH is equal to, remember, minus log base 10 of our pH. And in this case, our pH is, sorry, our H plus, sorry, minus log base 10 of our H plus concentration. Our H plus concentration is 1.61 times 10 to the power of minus 4. And then put that into our calculator. pH is equal to minus 3.79. We're not done yet. We're not done yet. Remember, the question was to calculate the change in pH when we've added the acid. They told us that our original pH is 3.8. Therefore, the change in pH is just pH is equal to 3.8 minus 3.79, which is equal to 0.01, which is actually what you'd expect, right? There's only a change. That's a very, very, very small change in pH. So it's what you'd expect because it's a buffer. And you're like, So if you get a value, a change of pH of 0.01, that is what you'd expect because this is a buffer, right? Buffers are meant to reduce the change in pH. They keep a constant pH by reducing the factor of change of pH, right? That's what they just try to halt that massive change of pH. They're not always going to be perfect changes, but remember you've added 20 centimeters cubed of 1 mole per dm cubed strong acid, right? And it's only changed by 0.01. So that's a pretty decent buffer, which is what you'd expect it to be, given the fact that you've added a lot of acid, right? And that's the end of the question. Because and that explains this. Look here, right? Even when we add more acid, right? Or for adding in this case, if you say this is a basic buffer, right, and we added acid, you're seeing here. As I said before, hit this part here. That's acting as a basic buffer. It's not the same buffers we have, but it's acting a base buffer. We're adding acid, right? And the pH is still decreasing, it's still slanting downwards, but it's only doing it very, very narrowly. And that's basically what's happening here. It's decreased by 0.01. The pH is decreased by 0.01, which is what we expect, but it's very minuscule change. So we've basically still maintained roughly a constant pH. So, and if you understand what's going on here, I've already explained it in the title in the start here, where just equilibrium is going to the right to reduce the sorry, equilibrium is shifting to the left because we've increased the H plus concentration. So we would, and sorry, there's been an increase to the H plus concentration, which has caused the equilibrium to shift to the left to reduce the H plus concentration by causing H plus to react with our propanoate ion, to form more propanoic acid to reduce the H plus concentration, and that's reducing the factor of change in pH. Of course, it's still a little slightly bit more H plus, but overall there's been a very minuscule change to H plus. So that's it. I tried to attempt this before. I think it's pretty much the same thing, isn't it? Really. I think I did, yeah. I think this one was probably a better explanation than the one I tried to do before. It's just a mock up. But anyway, hopefully this video was helpful. It's probably gonna be a very, very long video, but I'll try and make it in this case video that I'll try to make it in the title of this video that this is just my explanation. So that's it. Hopefully it was helpful, and bye.